Hi, welcome to this video of Singaporeans ramblings about nuclear technology. This is lecture or rambling number 8. So I think I have a little bit of a stuffy nose. I'm kind of under the weather now. My throat's feeling not too good, but yeah, just bear with me. Yeah, I still wanted to get these videos through. Hey, so let's just carry on. Last time we were talking about energy transitions in the nucleus. We see that usually these are mediated by photons or otherwise gamma rays. Okay, so an excited nucleus will emit gamma rays in order to release energy. So again, I'll just draw a nucleus here. Just draw a nucleus. Okay, if it's excited, the tendency is to put a star like this. Okay, a star like this. The excited nucleus will de-excite itself into a nucleus at a lower energy state. Okay, plus some gamma rays. Of course, there are multiple energy levels as you saw. Okay, I'm not going to be precise about them, but your energy levels can drop like 1 level, it can drop 2 levels, it can drop 3 levels even. And then from these levels, it can further drop down to what we call the ground state. Okay, so any of these transitions are possible so that you don't just emit a gamma ray of one single energy. It depends how excited the nucleus is, and that will determine the energy of the gamma ray output based on those fixed energy levels. Now, last time, we were talking about the nucleus itself being at specific energy levels, and they so-called emit gamma rays. So the model we have in mind, it's let's say you, I mean, if we had a nucleus, maybe 3 protons, 4 neutrons. Okay, this is lithium 7. Okay, and let's say you excite this nucleus such that maybe you can conceptualize it like this. Okay, you have a 3 proton, 3 neutron nucleus with a neutron actually so-called orbiting around the nucleus. Orbiting neutron. Okay, I mean, it's not exactly accurate, but you can think of it like that. So the neutron is orbiting the nucleus with this sort of a wave function. Okay, this neutron can be excited, and then when it de-excites itself, it's so-called release that gamma ray. Or actually, it'd be better if a proton is inside. Maybe I'll just do this. Okay, a proton orbiting this nucleus will be better. It's a better picture. Why? Because a proton is a charged particle. So when you like vibrate a charged particle, it creates disturbances in electric fields. So I guess that's an easier way that you can think. Yeah, it creates disturbances in electric fields, and then the so-called electromagnetic wave is emitted. So that's perhaps an easier way to conceptualize photon emission if you think about it in terms of waves, though probably in this sense not 100% accurate, because here it behaves more like a particle. But I digress. Just know that when you have individual protons de-exciting themselves in this so-called orbit, you do emit gamma photon. Okay, but as your nucleus gets larger and larger, okay, so these are what individual proton transitions. So this is one way gammas can be emitted when an individual proton in the nucleus goes from a higher energy level to a lower energy level. So that's one way you can get gamma rays out. So yeah, so we are talking about different nuclei, different nucleuses in excited states. Okay, excited states. Okay, you have one individual protons excited. Okay. Number two, we want to talk about collective motion. What do you mean collective motion? Yeah. What is collective motion? So basically, let's say you have uranium-238. Okay, you have uranium-238 right here. Okay, so what happens is that if you supply some energy here in the form of a photon, let's say a gamma photon or any other kind of photon, you can even knock another proton into this nucleus. You can knock a proton into this nucleus and then you will excite it just by transferring some kinetic energy. Okay, so we like to, I think, star it here. Okay, I can't exactly remember where you put the star, but that's a technicality. Okay, usually a star just means excited nucleus. Okay, how can this thing be excited? Now you have 238 particles right here in this uranium nucleus. So what can these 238 particles do? Okay, so let's say this is your uranium at your rest state, but you want to introduce some sort of vibrational energy. Okay, so if you introduce vibrational energy, your nucleus can stretch and deform like this, and so-called vibrate like this back and forth. It does a wobble. Okay, nuclear wobble. Okay, so that's one way. That's another way a nucleus can excite itself once there are many particles that are so-called vibrating at the same time. Okay, so it's not individual protons, neutrons getting excited, but this is them vibrating together like a wobbling motion. So there's so-called a wave, a vibration wave. Okay, a collective vibration wave of protons and neutrons that are wobbling together as if they're a liquid drop. Okay, okay, so this is vibrating as if they're a liquid drop. Okay, so so this is how we can excite larger nuclei like uranium, like lead. A lot of them can exhibit this sort of vibrations. Now, the amount of energy you use to excite individual protons to some excited state tends to be more than the energy you take to start to wobble a nucleus. Because this thing is just vibrating nuclei by each other, and yeah, this just is a wobble. Okay, it's a what we call collective motion. So the whole nucleus can spin around. Okay, the whole nucleus can spin around. So collective motion can be shaking, so to speak, okay, and spinning. Okay, so all of these things, these are just ways that a nucleus can so-called have excited states. Okay, and usually, again, I want to emphasize individual excited individual particle excited states. Okay, so this energy is greater than the vibrational collective motion, collective vibration excited state energy. Excited state energy. So now, so let me just put this here. So let's say the energy transition here is this energy single. Okay, your collective energy is going to be much less. Okay, so let's say this is the ground. Okay, E ground. Okay, for collective vibrations, the energy threshold you need is a lot less. E collective. So gamma rays need not be several MeV, so to speak, mega electron volts. They can be keV as well. So usually these gamma rays, okay, pardon me, these gamma rays here, yeah, in the KeV, low KeV range. Okay, so this usually this collective motion is usually for large nuclei. So these are what we call excited states. Okay, okay, so these are the two main ways nucleus can be excited. Main ways for nuclei to have excited states. Okay, so question is this. Okay, so we have nuclei in excited states, right? We have nuclei in excited states, and therefore they emit gamma radiation. How do they get excited in the first place? So I want to do this. How do nuclei get excited? Okay, how do nuclei get excited? Okay, so let me just give you a few scenarios. Okay, one is by photon absorption. Photons are basically light particles that carry the so-called electromagnetic radiation. So when the nucleus absorbs a photon, it gets excited. Okay, it can also get excited by de-excited by releasing photons. So this is very, very common. Next, okay, collision. Okay, if I want to be more precise, inelastic collision. Inelastic collision. So what's inelastic collision like? So let's say you have a proton. Okay, you have a proton hitting a stationary proton. So this is proton 1, this is proton 2. Okay. Okay, so proton 1 hitting proton 2. Okay. Under the conditions, well, here, momentum is conserved. And secondly, kinetic energy conserved. Okay. So for those of you unfamiliar, okay, momentum is always conserved. This is a basic physics principle, but is kinetic energy conserved? Okay, the most classic example is where, let's say, this proton is traveling at v1. Okay, okay, so this is before collision. After collision, okay, p1, p2, proton 2 will then travel off at a velocity v2, or rather v1. Okay, so before collision, the kinetic energy is what we call half mv1 squared, and after collision, energy, okay, assuming that this proton is at rest. Okay, so the kinetic energy before is half mv1 squared. Kinetic energy after is half mv1 squared. So basically, it's one ball knocking into another. All the kinetic energy is conserved. So pretend there is no friction. Okay, if you didn't understand the math, just roughly what this is saying is that there's no friction. Right? No friction. Okay, this is called elastic collision. Collision. Okay, elastic collision. Now, inelastic collision is the inverse case where there is friction. Is a friction. Okay, there is friction. So one example is, Okay, this time we have a neutron. Okay, it will scatter off, let's say 238, uranium-238. So the neutron has some kinetic energy, and then it scatters off like this. Okay, the neutron slows down, so to speak, because it transfers some of its kinetic energy to the uranium. And then after collision, this uranium, which uranium-238 has, which is modeled like a ball, it has some kinetic energy 3. So in an inelastic collision, the kinetic energy 1 is more than the kinetic energy 2, which is the kinetic energy of the neutron that just bounced off, plus Ke3, which is the kinetic energy of the uranium. So the uranium will fly off at some speed, and the neutron will also fly off at some speed. However, the sum of the kinetic energy for both the uranium and the neutron, when you sum them together, this is less than the energy here. Okay, where did this energy go? Okay, where did this energy go? Okay, where did the energy go? Okay, very simple. Remember just now I was talking about the vibration. Okay, so this is the uranium at rest, so to speak, or ground state. It turns into this vibrating nucleus like so that can wobble back and forth. So basically, this neutron supplied energy to this nucleus and it started to wobble. Okay, so if this wobbling motion is there, what happens? The most common thing is for it to undergo gamma decay. Okay, it starts going gamma decay, it releases the photon, de-excites itself. That means it gets rid of the excess energy and it comes back. So it will release this gamma photon. Okay, so this is the process of inelastic collision, okay, where the nucleus is excited and starts wobbling. Okay, and then after that, it will release some gamma energy. So that's another way you can have excitation. Now, third way, nuclear reactions. Okay, so this is where things get a little bit more exciting. All right, so nuclear reactions. So how do electrons get excited? I mean, the nucleus get excited. So first thing first, nuclear reactions. And I'm going to write nuclear reactions like this: neutrons plus uranium-238. Okay, so instead of just what do you call that? Instead of just instead of just bouncing off, it get absorbed. Okay, so what do you mean by absorption? Okay, so this neutron and this uranium-238, they combine. Okay, fuse. They fuse, they combine, or we call it neutron absorption. Okay, this is very important in nuclear reactions, neutron absorption. So what happens is that you have a uranium-239, and this uranium-239 tends to be excited. Okay, excited uranium-239. Okay, so when this uranium-239 gets excited, what happens? It will release, okay, it will release the gamma photon. Okay, what we call this reaction, there's a special name for it. We call it N-gamma reactions. So this is important in nuclear engineering. Okay, important. Okay, N-gamma reactions. So basically, neutron is absorbed, the nucleus goes into an excited state, and then it will de-excite itself by releasing a gamma photon or a few gamma photons. Okay, so this is what we call N-gamma reaction. Okay, so take note of this. This is extremely important. Okay, so why did this neutron fusion process result in an excited state? Okay, why did neutron absorption? Okay, we call it neutron absorption. We don't call it fusion. Okay, but it is effectively somewhat of a fusion between the neutron and some other nucleus. Absorption result in excited state. Okay, it boils down to forces. Okay, boils down to forces. So the neutron and the uranium-238. Okay, neutron and uranium-238. Okay, if you bring them close enough, there is a strong nuclear force. Strong nuclear force. Okay, so there is going to be some sort of an attractive force. Okay, there's an attractive strong nuclear force that glues these two objects together. Okay, so basically, if there's an attractive force and some distance between them, okay, so if you have attractive force plus separating distance, what's going to happen? Okay, so easiest way of thinking about this. Let's say you have a 50 km boulder, 50 km wide boulder. However the shape is, it doesn't matter. You just have a big boulder like this. Okay, let's put it at a distance from, let's say, 30 km into the sky, and let's put our beloved planet Earth here. Okay, Earth. Okay, what's going to happen? Okay, you have attractive force of gravity. Force of gravity. And you have separating distance here. Okay, you have a separating distance here, let's say 30 kilometers. Okay, and suddenly you put them together. What's it gonna do? Of course, you can say that this boulder will orbit around Earth, but let's say it doesn't. Let's say there's no orbit and it just starts falling towards the Earth. What will happen? Okay, it will gain more and more speed. Okay, it will gain more and more speed, and by the time it hits the Earth's surface, it'll be going very fast. So what happens when a very fast object hits another stationary object? Okay, in this case, Earth. Okay, boom. Okay, boom. Okay, so what's this mean? Heat energy is released. Along with sound energy, shock waves, and general mayhem for everyone else living on Earth. Okay, it's not going to be a good day. Okay, so this is I think premise of a lot of movies. Okay, but basically, when you put two objects together, or rather you have two objects with an attractive force, and you put them sort of far enough, and you let them come together, there's going to be energy released. Okay, that is the basic principle. Okay, you have energy released, and the same thing applies to these two objects. So imagine this neutron was your asteroid, and this or asteroid or boulder, and this uranium-238 is going to be planet Earth. Okay, you have this strong nuclear force that's going to attract both of these objects. You separate them by some distance and suddenly you put them next to each other. Boom. Okay, there's going to be a lot of energy that's released. Okay, same idea here. So the energy released is going to cause a lot of mayhem on the surface of this neutron, no, this uranium nucleus, and it's going to be what we call excited. Okay, it's going to have a lot of energy, just like this analogy here. You have asteroid going on Earth, a lot of heat energy is released. Same idea here. This nucleus will be in mayhem, or what we call excited state. So it can wobble. There's some some particles that can jump to some excited state, and generally speaking, to de-excite itself, it can release a gamma photon. It can release a gamma photon. So this is one example of many where you have nuclear reactions causing nucleus to be in excited state. Now, the converse is also true. The converse is also true. Okay, let's say you have uranium-238 and it undergoes usually what we call alpha decay. Now, alpha particles means to say it's a helium particle and it will be released out. And what will have? Okay, it will release out and you will get thorium. Okay, thorium-234. When you look online, okay, you can search for this thing called uranium decay chain. Okay, uranium decay chain, and you can just look at the thing that uranium decays into. I'm not going to so-called I'm not going to bring you through all of this, but this is kind of important. Okay, so uranium-238, there is a decay chain. Right, so all these decays, they can actually supply energy as well. Okay, so anyway, this is an example of what we call alpha decay. Now, basically, what sometimes happens is that this will be excited. This thorium here may be in an excited state. Okay, now that isn't always true. Okay, I think I have picked the wrong example here. I went to go and check it out and oops, okay, maybe this was not the best example. A better example is what I think the most common one is cesium. Cesium-137. So I think forget this. This is a decay reaction, a very important decay reaction, but not the one I want to use here. Okay, cesium-137 can decay in what we call beta decay. Okay, if you take a look here, cesium-137 can decay into this barium-137. Okay, this is Wikipedia. I prefer not to use Wikipedia, but that was what happened. So basically, this doesn't always happen, but it does happen enough. Okay, so basically, there's a beta decay here. Cesium goes into barium. This barium is actually excited. And what does it do? It emits gamma rays. Okay, sometimes they call this barium-137M. It's M for metastable. Basically, what it does is that whenever there is this sort of nuclear reaction, okay, in this case, it's a beta decay. Okay, there is some excess energy in this nucleus that allows it to be excited. Okay, the result of this excitation is that it will try to de-excite itself. It will release gamma rays. So there are these kind of nuclear reactions that cause this it causes the nucleus, the resulting nucleus, to be excited. Okay, it will cause this nucleus to be excited. Okay, barium is a group 2 metal. So what happens here is that one of the neutrons inside cesium, it converts into a proton and a electron. Okay, the electron is this beta minus particle. It will be emitted at very high energies, and it will leave, sometimes it will leave this nucleus in a more excited state. Because the other way is for this beta particle, the electron to carry away all the energy, and that is the second decay mode. Okay, so sometimes it happens the first way, sometimes it happens the second way. All right, so this beta will have higher, this beta here will carry away all the energy due to the decay. Okay, and yeah, and it will carry all the way away all the energy of the decay, and then there will be no gamma ray emitted here. So gamma rays, again, you emit them when you excite the nucleus. Okay, so but what the main point I want to bring across is that nuclear reactions in general, they can excite the nucleus, and that's why you release gamma rays to de-excite it. Okay, so what we talked about extensively here is gamma decay. Okay, what we talk about extensively here is gamma decay. Okay, gamma decay. And this is just one of many ways, one of more than one ways, one of several ways that a nucleus can de-excite itself. Okay, so there are, of course, other ways of decay. Like you saw before, there's this thing called alpha decay. And that's where I want to say this uranium-238, it gives out this helium particle, which is the alpha, plus thorium-234. Okay, beta decay, as you saw just now, cesium-137, which is one of the problematic radionuclides after a fission test, or in some nuclear disasters like Chernobyl, Fukushima. This was one of the radionuclides that was a little bit more problematic. What happens is that it can decay into a particle at an excited state. So I like to put this star down here, and then it will decay back to barium-137 plus this gamma ray. Okay, so this is gamma decay. All right. So so we've gone through gamma decay a little sort of in detail. Okay, the whole nucleus may be wobbling and then de-wobble itself by releasing the gamma ray. Okay, so this is so-called covered by quantum mechanics, or the Schrodinger's well, it can be partially explained by Schrodinger's equation. Okay, alpha decay can also be partially explained by Schrodinger's equation. Okay, why did I say that? Okay, so the way we think about alpha decay, or at least way we can think about alpha decay, is that for this uranium-238, okay, there is this alpha particle, this helium nucleus that's orbiting around this thorium nucleus. So okay, you have a 234 thorium, and then this helium, okay, helium-4 is sort of orbiting around, or rather, the more quantum way to put it is the wave function. Okay, so it will be waving its way around, and it doesn't have enough energy to escape by default, but because of the quantum weirdness, you actually have a non-zero probability of this particle escaping. So let me draw these energy barriers, and there is some finite probability that this helium particle can tunnel through because of its wave nature. Quantum tunneling. Okay, quantum tunneling is one way we conceptualize alpha decay. So this alpha particle basically tunnels through to get to the outside. And that's how you get alpha decay. So why does alpha decay happen? So the way we like to think about it is that because these waves leak through or tunnel through the strong nuclear barrier, it's able to get through even though traditionally it doesn't have enough energy to get out. Okay, but of course, this is because there's a finite barrier here. There's a finite barrier, so it's not infinite. If the strength of the barrier is not so high or not infinite, the wave can leak through. If the strength of the barrier is weaker, there's a higher chance that this particle will leak through because it will not be able to contain the probability wave as well. So that's the conceptual way of explaining these things. Okay, so alpha decay can be explained or conceptualized via quantum tunneling. Okay, and both of these, alpha and gamma, you can sort of use Schrodinger's equation as a mental framework to think about it. Okay, for beta decay, it is its own special thing. Okay, beta decay is its own special thing because it's mediated with the weak nuclear force. Okay, beta decay is special, okay, because it relies on weak nuclear force. Okay, so I think I want to sort of rest today because I'm not feeling well. I'll not keep going on, but there are some good references. Okay, for this weak nuclear force, you should be able to conceptualize it, and the best way to conceptualize it is using this standard model for particle physics. Okay, well, we are getting really deep into physics here, the more exotic bits, but these are the things that help us to explain what is going on. Okay, now you talk about gluons, photons, bosons, and gravitons. Okay, all these are like physics stuff that I guess the nerds are talking about. And I guess by definition, because I have a PhD, I'm sort of a nerd as well. But this is, to be fair, not my specialty. Okay, I can tell you a little bit about it, but I will not be able to tell this to you as good as someone who does a full physics degree. Okay, I did engineering more, so I know just enough to study reactors, enough of the physics to study reactors, but I do not study so much of the physics as to explain this to you in detail. Okay, of course I took a course on nuclear physics, but that was a while ago, so I need to refresh my memory myself. Okay, now to look back at those class notes again. It's been many years, but yes, it's stuff I sort of touched before. Okay, so anyway, I'll leave this to the next rambling / lecture, and I'll be taking a break now. Thanks for watching.